Welcome, my friends! In this video, we will be discussing the paired t-test. The paired t-test is a hypothesis test that involves drawing two samples, where each observation from the second sample is dependent on an observation from the first sample. These types of situations happen naturally in before and after scenarios. Examples include measuring blood sugar levels before and after medication, or perhaps pre- and post-test scores administered to evaluate learning. The actual hypothesis test is not applied to either of the two samples individually, but rather the difference between the two samples. For example, if sample 1 represented pre-test scores and sample 2 represented post-test scores, the hypothesis test would be performed on the difference in scores, post scores minus pre-scores. We can calculate statistics based on the difference column, such as the mean and standard deviation, but we label these symbols with a subscript d to signify that they are related to the difference of the two dependent samples. Here are the forms of the left-tailed, right-tailed, and two-tailed paired t-tests. Mu sub d is the population mean difference, which is the parameter we are testing. Theoretically, we could test whether or not the mean difference differs in some way from a value other than 0, but using 0 as the hypothesized value is the most common. Since we use the t-distribution, t equals 0 is in the middle, and the p-value is either in the left tail, right tail, or the sum of the left and right tails together, depending on which of the three types of tests is being conducted. There are a number of assumptions about the data that are needed in order to use the paired t-test. First, a random sample must be taken. Secondly, if the distribution of the differences is normal, any sample size will work. Otherwise, the number of differences, n sub d, must be at least 30. This is so that the central limit theorem will apply, meaning the distribution of x bar sub d will be approximately normal. In order to complete the paired t-test, we must calculate a test statistic using this formula. X bar sub d divided by s sub d divided by the square root of n sub d, where x bar sub d is the mean of the difference variable, the third column of data after we have subtracted the numbers from the two samples. S sub d is the sample standard deviation of the difference data, and n sub d is the number of data pairs we have, which is the same as the sample size from each sample. Note that you will sometimes see this formula expressed with d bar instead of x bar sub d, but they both represent the same thing, the sample mean of the differences. Also remember that we need degrees of freedom to use the t-distribution, which are equal to n sub d minus 1. Okay. Now, if you are looking at this formula closely, and you're a statistics whiz who knows your test statistic formulas, you might be feeling a little bit of deja vu. Where have you seen this formula before? Oh yes, this is just the test statistic for the one sample t-test, just with d's added onto everything. In fact, that's all that a paired t-test is. It's just a one sample t-test applied to difference data. So if you understand the one sample t-test, the paired t-test should be easy to learn. The only difference is that we have mu sub 0 in the one sample t-test formula, which is missing in the paired t-test formula. The reason is, we typically use a hypothesized mean value of 0 for the paired t-test, which eliminates this term in the paired t-test formula. Let's look at an example. Professor Luke gave 10 random students a test about basic statistics terminology, both on day 1 of his statistics class and on the last day of class. Luke would like to think that his students will score better on the post-test than on the pre-test. Using the given data, test the hypothesis at the 0.05 level of significance. Assume the distribution of both the pre- and post-test scores is approximately normal. If we glance at the data, notice that each pre-test score can be paired to a post-test score in the second sample. Row 1 represents student 1's pre-score test paired with student 1's post-test. Row 2 represents student 2's pre-test score paired with student 2's post-test score, etc. In other words, every observation in sample 1 has a corresponding paired value in sample 2, which is one of the hallmarks of the paired t-test. Note that the assumptions for our test are met, as firstly, we have a random sample, and secondly, we have a normal distribution for both our pre- and post scores, which means that our difference variable will also be normal. Next, we can move on to the 3 steps of our hypothesis testing procedure. Step 1. The null and alternative hypotheses. Each hypothesis starts with mu sub d, and if we reread the problem, we see that Professor Luke would like to think that his students will score better on the post-test than on the pretest. Let's define our difference variable d as the post-score minus pre-score. This means a positive mean difference would signify improvement. So therefore, the alternative hypothesis is mu sub d is greater than 0. Remember that the alternative hypothesis typically relates to what the researcher would like to prove, which in this case is that the mean difference is positive. The null hypothesis always contains an equal sign, so we have mu sub d is equal to 0. Before we move on to step 3, you might notice that we don't have any of the statistics, so we'll have to calculate them ourselves using our handy-dandy TI-84 calculator. To do that, we must utilize the stat list. Press Stat, Enter for Edit, scroll over to List 1, and press Clear and down arrow to clear the list. And then hover over to List 2, press Clear, and down arrow to clear that list. Now enter the sample data into the two lists, pre-score in List 1 and post-score in List 2, pressing Enter after each amount has been entered. Once all the data is in there, hover over List 3. Press second, 2 minus second, 1, which gives you List 2 minus List 1, or in our case, post-score minus pre-score, the difference of the two variables. Press Enter, and the difference between the two lists will be in List 3, which we can verify by checking a few of the numbers. 66 minus 60 is 6, 52 minus 48 is 4, etc. Now press Stat again, arrow over once to Calculate, and choose one variable statistics. Press second 3 to change the list to List 3, since that's where the difference data is. Leave the frequency list blank, and press Enter to calculate, and we will have the descriptive statistics. On a TI-83, you simply have to put List 3 after one var stats. Again, you can get List 3 by pressing second 3. We need X bar, SX, and N, but the calculator doesn't know that these values are calculated based on difference data, so there is no subscript D. So for us, X bar sub D is 3.5, S sub D is 5.5628, and N sub D is 10. We also know that the degrees of freedom are N sub D minus 1, which is 10 minus 1, or 9. Okay, now we can move on to step 2, calculations. Here is the formula for the test statistic, which becomes this when we plug in all the numbers into the formula. Typing into the calculator, we have 3.5 divided by, open parentheses, 5.5628 divided by the square root of 10, and then close parentheses, press Enter, and we get 1.99 for our test statistic. At this point, it's a good idea to draw the distribution. The t-distribution has a mean of 0, and we just calculated that the test statistic is 1.99. We must calculate the p-value, which is the area in the right tail of the distribution, which I have shaded in green. We can find the p-value using the calculator by going to Second, Distribution, Option 6 for t-CDF. The lower bound is the lower boundary of the shaded area on the graph, which is our test statistic of 1.99. The upper bound is positive infinity, which we can put in as 1,000, which is plenty large enough. The degrees of freedom are 9. When we press paste, we get this screen. On an older calculator, like a TI-83, match this output. t-CDF, 1.99, 1,000, 9. Press Enter, and we get the p-value of 0.0389, rounded to 4 decimal places. This is the area in the right tail of the distribution, and is the probability of sampling a mean difference of 3.5 or greater, assuming that the mean difference really is 0. Step 3. Decision and conclusion. If the p-value is less than or equal to the level of significance alpha, then we reject the null hypothesis, and if the p-value is greater than the level of significance, we fail to reject the null hypothesis. Like I always say, if the p-value is low, the null has to go, and if the p-value is high, the null will fly. In our case, the level of significance is 0.05, and the 0.0389 p-value is less than or equal to the 0.05 level of significance. The p-value is less than or equal to the level of significance, so we reject the null hypothesis. The p-value is low, so the null has to go. Our conclusion is that at the 5% level of significance, there is enough evidence to suggest that the post-test scores are higher than the pre-test scores in Professor Luke's class. And we are done. Alright, my friends, that wraps up our discussion of the paired t-test. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.